So I'll talk about volcanic debris avalanches and their dynamics. The picture on the screen is not from my study area, but it's quite illustrative, so that's why I'm using it for the introduction. Volcanic debris avalanches initiate from the collapse of partial collapse of volcanic edifices, and they initially propagate as slides and progressively evolve into flows. They are characterized by high mobilities, while theoretical concepts and models of their propagation are unable to reflect all the observations of their structure and sedimentology made in the field. However, it's important for all models of their propagation to be consistent with what we observe in the field. The scarcity of recent events means that there is a lack of fresh, well-preserved deposits, and older deposits tend to be indurated, which means that it's harder to study their sedimentology and especially their class size analysis. In this study, we examined two such indurated deposits in the Spanish Canary Islands, the Tentenihuada debris avalanche on the island of Gran Canaria, and the Abona debris avalanche deposit in Tenerife. Both of these present a great study opportunity due to their good preservation and exposure of their deposits. Both deposits exhibit the two characteristic volcanic debris avalanche fascies, which are the block fascies here on the left, which is composed of undisaggregated or poorly disaggregated portions of the original edifice, which in some cases even preserve their original stratigraphic sequence in their interior. And the second fascies is the matrix-rich fascies, which is a heterolithic, poorly sorted mixture of clasts and matrix. Even though both deposits present these two fascies, they're very different in terms of their structure. And that is because they reflect on different propagation processes, and their comparison allows the evaluation of the process and the dynamics that created them. Therefore, in this presentation, I have divided it in three parts through which I'll talk about first the methodology which allowed the evaluation of the two indurated deposits. Secondly, I'll present the observations and analyses which enabled us to generate conceptual models of their propagation. And finally, I'll present the comparison, which leads to the conclusion that lithological properties of such avalanches play a principal role in their propagation mechanisms, dynamics, stress distribution, and this reflects in their structure and sedimentology. For the methodology, we initially carried out a detailed mapping of their deposits in terms of the distribution of their features and fascies distribution. And then because class size analysis using conventional sieving was not an option, we used a new methodology which uses structure from motion photogrammetry. We did this on two scales, and we generated samples on the larger outcrop scale, which was better for representing larger clasts. And because photogrammetry uses information from multiple photographs, it did not compromise image quality. On the smaller scale, we used smaller sample windows with better resolution, which were better for the smaller clasts. And then the combination of the two allowed us to consider a wider class size range. Just because it's interesting, I wanted to say that we've used this methodology also, the photogrammetry methodology also in the field to analyze the results of analog experiments of granular avalanches. So the first deposit we examined was Tentenihuada on the east of the island of Gran Canaria, and is importantly not dominated by lava lithologies with only a minor component of pyroclastic material. The deposit exhibits a network of portions of the original edifice or blocks, which in some cases preserve their original stratigraphy. These blocks are displaced in relation to each other by normal faults, and in general there is a ductile behavior which is very obvious in the deposit. The interior of blocks is in some cases jigsaw fractured, so it preserves this fractured texture, but the component clasts remain in place, and they adopt this texture which means that they were fractured by the initial collapse, but there was a lack of agitation later during the propagation. So the findings suggest that the part of the edifice which collapsed suffered a coarse disaggregation initially, and then the fractures generated were activated as normal faults, allowing the material to spread and the center of mass to lower. This focused the shear stress in block boundaries and meant that the interior of blocks remained relatively well preserved. And therefore we describe this mode of displacement as normal fault accommodated extension. And it resulted in this deposit, which more closely resembles a non-volcanic rock slip deposit rather than a classic volcanic debris avalanche. The second deposit was Abona on the south of the island of Tenerife, and in contrast to Tentenihuada, it was composed of weaker pyroclastic material, and all the material in the deposit is characterized and microfractured. However, lithological units preserve their lithologic homogeneity, and where they mixed and intrude other units, they adopt this form of fluidal features, which looks like the mixing of viscous fluids. The matrix-rich facies is a much more major component of this second deposit compared to the Tentenihuada. Class size analysis suggests that there is no systematic evolution in the class size distribution or the proportion of matrix relative to crusts in these deposits. And this is the result of the chaotic and systematic distribution of shear, which is not focused in any one location and is periodically accommodated in different places according to the self-weight of the mass during propagation. Therefore, this second debris avalanche, which was composed by weaker pyroclastic material, disaggregated into a granular mass and propagated as a fluidized granular avalanche with shear distributed throughout the mass in periodic networks and wasn't focused in any one specific location. And we have used experiments as well to evaluate this kind of granular avalanche, which is not which is more disaggregated than the first one I presented. So the comparison of the two suggests that the two debris avalanches propagated under very different dynamics and produced very different deposits. This is the result of their different material properties, and it suggests that lithological properties of volcanic debris avalanches play a major role in their propagation mechanisms and dynamics, and this reflects in their deposits and the sedimentology and structure, and therefore from that we can understand what their dynamics were. In the case of Tentenihuada, the component material did not disaggregate into a granular mass, and therefore it did not fully evolve into a flow. It rather displaced as a normal fault accommodated spreading, resulting in a not very disaggregated deposit. In contrast, Abona was disaggregated into a granular mass, which could become, with particles free to engage in collisions, become agitated, and it propagated as a fluidized granular flow. Therefore, lithological properties, as I said, potentially play a principal role in the propagation of such events. This study highlights the importance of dedicated field studies for understanding the dynamics of volcanic debris avalanches and other similar events. And it also offers a methodology which allows the examination of more indurated deposits and understanding the evolutions, the dynamics of the processes that generated them. Thank you very much.